Lesson: Probability and Statistical Models in AI. Probability and statistical models form the backbone of artificial intelligence, providing the tools and methodologies to handle uncertainty, make predictions, and infer patterns from data. Understanding these concepts is crucial for professionals seeking to implement AI solutions effectively. This lesson delves into the mathematical foundations of probability and statistics within AI, offering actionable insights and practical tools to enhance your proficiency in this area. Probability, at its core, is the measure of the likelihood that an event will occur. In AI, probability models are used to manage uncertainty and represent the degree of belief in various hypotheses. One of the most fundamental applications of probability in AI is in Bayesian networks, which provide a graphical model for representing the probabilistic relationships among a set of variables. These networks are instrumental in decision-making processes, allowing AI systems to update predictions as new data becomes available. Consider the practical application of Bayesian networks in medical diagnosis. A Bayesian network can model the probabilistic relationships between symptoms and diseases, enabling the system to infer the most likely illness based on observed symptoms. For instance, if a patient presents with a cough and fever, the network can calculate the probability of various diseases such as the flu or pneumonia, providing a robust framework for diagnosis. Tools like Netica and Jenny facilitate the construction and analysis of Bayesian networks, allowing AI professionals to implement these models efficiently. Statistical models in AI are equally pivotal, providing a framework for making inferences about data. Linear regression, for example, is a statistical method used to model the relationship between a dependent variable and one or more independent variables. This model is frequently employed in predictive analytics, where the goal is to predict future outcomes based on historical data. In the context of AI, linear regression can be used to forecast sales, optimize marketing strategies, or even predict stock prices. Beyond linear models, logistic regression is widely used for classification problems, where the objective is to predict categorical outcomes. This statistical technique estimates the probability that a given input belongs to a particular class, making it invaluable for applications such as spam detection or credit scoring. The practical implementation of logistic regression can be facilitated using machine learning libraries like TensorFlow or scikit-learn, which provide pre-built functions to train and evaluate these models with ease. Another essential statistical tool in AI is the decision tree, a model that uses a tree-like graph of decisions and their possible consequences. Decision trees are particularly useful for classification and regression tasks, offering a transparent and interpretable method for decision-making. For instance, in a business context, a decision tree might be used to determine whether a customer is likely to purchase a product based on demographic information. Software like R and Python's scikit-learn library includes modules for constructing and visualizing decision trees, enabling professionals to leverage this model effectively. The power of probability and statistical models in AI is further exemplified by ensemble methods, which combine the predictions of multiple models to improve accuracy. Random forests, an ensemble method, build multiple decision trees and merge their predictions to produce a more accurate and robust model. This approach is particularly effective in handling overfitting, a common challenge in machine learning, where a model performs well on training data but poorly on unseen data. Random forests have been successfully applied in diverse fields, from healthcare to finance, providing superior predictive performance. In real-world AI applications, handling uncertainty is a critical challenge. Probabilistic graphical models, such as Markov chains and hidden Markov models, offer a structured approach to modeling stochastic processes. These models are extensively used in natural language processing, where they help in tasks like speech recognition and part-of-speech tagging. The versatility of these models lies in their ability to represent sequential data and capture the dependencies between observations, making them indispensable in time series analysis. A practical framework that integrates probability and statistics in AI is the probabilistic programming paradigm. This approach allows for the creation of complex models that can reason about uncertainty and make predictions. Tools like PyMC3 and STAN provide a platform for building and training probabilistic models, offering a high-level interface for specifying and solving Bayesian statistical models. These tools empower AI professionals to handle complex probabilistic reasoning tasks, from recommendation systems to anomaly detection. To illustrate the application of these concepts, consider the case study of a retail company aiming to optimize its inventory management. By employing probabilistic models, the company can forecast demand for different products based on historical sales data, seasonal trends, and economic indicators. Statistical techniques like time series analysis can be used to model the temporal dependencies in sales data, while Bayesian networks can incorporate external factors such as promotions or competitor actions. This integrated approach enables the company to make data-driven decisions, reducing stockouts and minimizing excess inventory. The effectiveness of probability and statistical models in AI is underpinned by their ability to generalize from data and make predictions about unseen instances. However, selecting the appropriate model and tuning it for optimal performance requires a deep understanding of the underlying mathematical principles. Cross-validation, a statistical method for assessing how the results of a model will generalize to an independent dataset, is crucial for evaluating model performance and preventing overfitting. By partitioning the data into training and testing sets, cross-validation provides a robust framework for model selection and evaluation. Moreover, the integration of domain knowledge into statistical models can significantly enhance their predictive capabilities. For example, in the financial sector, incorporating economic indicators into a regression model can improve the accuracy of stock price predictions. Similarly, in healthcare, embedding clinical expertise into Bayesian networks can enhance the system's diagnostic accuracy. This synergy between data-driven models and domain expertise is a hallmark of successful AI implementations. In conclusion, probability and statistical models are indispensable tools in the AI practitioner's toolkit, offering a robust framework for handling uncertainty, making predictions, and extracting insights from data. By leveraging these models, AI professionals can address real-world challenges, enhance decision-making processes, and drive innovation across various industries. The practical tools and frameworks discussed, including Bayesian networks, regression models, decision trees, ensemble methods, probabilistic programming, and cross-validation, provide a comprehensive foundation for implementing AI solutions effectively. Through a deep understanding of these concepts and their applications, professionals can elevate their proficiency in AI and deliver impactful results.